Welcome. In this video I'm going to show you how you can perform a post-hoc goodness-of-fit test using Pairwise binary test and Microsoft Excel without using my add-in. I have an add-in that can actually just have a function that can do this in one go, but in this video I won't be using that. Now, alternatively, you could be using Pairwise goodness-of-fit test, or you could be using residual test if you're only interested to know if the observed counts would be significantly different from the expected counts. The pairwise indicates that we're going to be looking at every possible category combined with any other category. So to give you an example, I have the binomial one over here. I have some data in column A. I determined the number of categories and counted how often each of these actually occurred. So as you can see, I had 5 categories, and I assumed the chi-square test was significant, and I would like to know which of these categories differ from each other significantly. And one way to do that is a pairwise binomial test. So I list the expected counts that I had, or you could list the expected proportions. In this case I had expected counts and then simply divided that by the grand total. Otherwise, if you have expected proportions, you can multiply them with the grand total. If you don't have expected counts and you just expected each of these to be equal, take the sum of these and divide it by the number of categories, and that will then be the expected count for each category. I've listed each pair, so I started with pair 1 and 2. As you might notice, I made a small little index over here, and just to show you the formulas, they're over here, but I can also show you here. Of course, this simply is going to check if I need a next row and just adds one, and that way I can get all possible comparisons. This is using a VLOOKUP. As you might notice, my system is using a semicolon to separate parameters. Yours might be using a comma. I'm looking up this index in that table over here, and it returns to me the second column. I'm using dollar signs to fix that error so I can copy it, and I just want exact matches, so a 0 over there. Similar for the second category, so I now know that this will be married versus divorced. I also look up the counts, again similarly with a VLOOKUP, and the number of pairs is simply the sum of these two. The observed proportion is simply the sample size divided by the number in the pairs, and the second one is then simply 1 minus the first one. I'll do that for each category, and then I need to adjust these expected counts, because these two, for example, married and divorced, won't sum up to 100%. So what I'll do is I'll first look up the two percentages for each of the two categories, again simply using a VLOOKUP, and then what I'll do is I'll simply take the first one and then divide it over the sum of the two. That way the ratio stays the same. Again, for the second category is then simply 100% minus the expected proportion of the first category. So these pairwise will all sum up to 1. Then I'll look for the category with the smallest sample size. So these were the n in the pair actually. So this is n in the pair. The minimum of the two, so that's the minimum of these two. And then which one of those its corresponding expected proportion, which is simply looking if this 314 matches this one, then take the first, otherwise take the second. The observed proportion of the minimum is similarly done. I'll simply look it up and then check if I need the first one or the second one. Once we have all that, I just look at the number of pairs, which can also be obtained by taking the combinations function, which is the binomial coefficient of the number of categories we originally had, and choosing 2 of those. So in this case 10, and that should match with the length of this table, which indeed, as you can see here, is 10. Now, for the one-tailed probability, what we can do is use this fancy formula. It depends on if our expected proportion is less or higher than our observed proportion. So that's why there is a bit of an if, and we use the binomial distribution function for this. So that's being done over here. You can also look at my one sample binomial test video where I explain this a little bit more, but that's in essence what this function is doing. Now, unless your expected proportions are 50% each time, you shouldn't actually be simply doubling these, although it's one strategy that's sometimes done, so simply doubling it. And because we're doing multiple testing, we actually then multiply the two-sided significance with the number of tests that we have. So that would then be a Bonferroni correction. There are other variations, but this is the most simple one. Of course, this could then become bigger than 1, so and that's impossible for a proportion, so we leave it. We select the minimum of 1 or this one times, in this case, 10. Now we could use the equal distance method, which is already better than the doubling. What I do here is I first determine the expected count of the minimum value, which is simply the expected proportion that we had over here multiplied with the sample size of the pair. Then I look at the difference with the observed one, which was over here. And then I actually add it, so I get the count that's in the other direction. So that has an equal distance of with the first one we calculated for the one-tailed. So the one-tailed in the other direction has then similar function as the first one, but now as you can see it's actually the other way around. So that looks like this. Then the two-tailed is simply the one-tailed plus the one-tailed in the other direction, and again we can so that's simply a plus, and then we can take again the corrected version for family-wise error rate correction, as it's formally called, using Bonferroni, and we have our adjusted p-values. So over here we can see that this one is above the usual threshold of 0.05, so these two would not be significantly different. And this one is below, so these two would be significantly different. Another method would be the small p method, where you simply list all possibilities, calculate the probability mass function, and then check which ones, sum all the ones that are less or equal to the observed one. Besides doing a binomial test, we could of course also do a z-test. So similar as before, here I actually made a small little table out of it, and as you can see this simply looks up the sample size for the pair by adding the two observed counts. Here I'm using a fixed 0.5 as an expected proportion for each, and then I'll multiply that with our sample size. Then for a score test, which actually will then be the same as the so-called standardized residual or adjusted standardized residual test. And that will actually give my standard error. So I'll take the mu value, which is this one over here, and then multiply it with 1 minus the expected proportion. Or doing a wall test, which is similarly, but then takes the observed counts, which is then the over here, the observed counts, over here. So that is very similar, but then flipped around. Then the z value is actually the difference divided by that standard error. So that's simply going to be the difference between the observed count and the expected count, and then divided by this one. We then multiply this, we get the probability of this using a normal distribution or standard normal distribution. We take the z value, the absolute value of it, put a negative in front of it, and then times 2. So we have a two-tailed version. And then again, to adjust, we'll use the Bonferroni adjustment, and I'll simply do the minimum of actually the number of tests that we had, that's all of this, times the p-value we actually found. Alright, I hope this was helpful, and thank you for watching.